Good evening, ladies and gentlemen. Let us figure out the heat exchange rate for co-current and countercurrent heat exchangers in terms of LMTD, which is log mean temperature difference. It's obviously going to be a log and a mean and a temperature and a difference. So let's start by talking about heat exchangers. What do they look like? What do they do? They exchange heat, right, between two medias. We've got, can I just draw a cylinder and it'll draw it for me? Nope, that's a square. Okay. All right, here's our heat exchanger. Beautiful. Gorgeous. It's not really, I mean, I guess if you look at it, it's got perspective. Whatever. Let's do co-current, right? We're going to do co-current heat exchanger. Co-current heat exchanger involves your cold media going in to your heat exchanger and your hot media going the exact same direction in the little tube in the middle. What's going to happen is in a certain area, dA, you're going to have your hot media transfer heat into your cold media, right? So as you go down the heat exchanger, your cold temperature, your temperature going out is going to be hotter than your cold temperature going in, versus your hot temperature coming out is going to be colder than your hot temperature coming in. Now, for a countercurrent heat exchanger, it just goes the opposite way. Like it just moves the opposite direction. So, yeah, that's heat exchangers for you. Oh, why did I turn off my iPad? Hey! Let me log back in. Hey! Oh, I have to. Great. Give me a second. Share my screen. Share without audio. You don't want to see the back of my head. This is Cody from Star Wars. I don't know. I think he's just from the Clone Wars. I don't know much about him. He's sitting on a candle, which is not my room. My room's pink, not blue. Okay, so we're going to find the heat exchange rate. So we want to look for our heat, and we're going to use a universal heat transfer coefficient. We're just going to call it U, universal U, right? And that is going to be multiplied by our temperature of the hot area minus the temperature of the cold area, because heat is exchanged from the hot to the cold with respect to that area. If you're anything, if you're a sane person, you're gonna go, oh, I want to do an integral. I want to take an integral of this. Oh, wait, this is in terms of area. All this is going to do is absolutely nothing. I'm not going to solve for what I want or solve very nicely. You know, you don't want to be here so bad. You want it to work out so bad, but it can't. It can't. We got to look at it in a different way, right? So we are going to relate heat. We're going to use the equation Q equals mass flow rate times heat capacity times the change in temperature to find the integral for our heat exchange rate. How are we going to do that? Well, we're going to create an expression saying the mass flow rate of the hot minus the mass flow rate, or the heat capacity of the hot stream equals capacity of the hot. And the mass flow rate of the cold minus the heat, times the heat capacity of the cold equals capacity of the cold. So we take the derivative of our heat, and we find that the mass flow rate of, say this is for H, times the heat capacity of H, times the derivative of temperature of H. This is going to be our little funny variable right here. So we can find that change in our heat is equal to CH times change in our heat. And that'll be the same for the cold. Cold never bothered me anyway. It's funny how some distance makes everything seem strong. The fears that once controlled me can't get to me at all. So then we do the change in heat. All right, we're going to write this down. The change in heat is equal to our universal heat transfer coefficient multiplied by the change in temperature multiplied by that change in area. Yes, it is. And so the derivative of the change in temperature is sorry, I almost killed you, is equal to that change in temperature. And looky here, what do we have here? We have that change in temperature. So plugging that in, right, we're going to plug that in. So that means dividing each of these by C value. So we get the change in temperature. The change in temperature is equal to, we forgot something. This is negative. Anyways, so this is going to be negative Dairy Queen divided by CH minus our change in heat divided by our CC. Sorry, I'm really trying to kill you. My sleeves are just hitting it. Let's factor out, you know what, I'm going to write it to the side. Let's factor out that Dairy Queen. Look at that Dairy Queen. So we're going to just get that, and let's do negative Dairy Queen. We're factoring out negative Dairy Queen. So now we just have 1 over CH plus 1 over CC. Beautiful. And look at that. Dairy Queen, our change in heat capacity is right there. So let's just plug her on in. And we get change in temperature is equal to our universal heat transfer coefficient multiplied by our change in temperature. And by this. And multiply by that the change in area. So let's divide over our change in temperature to get all our like variables together. So we have 1 over our change in temperature times the derivative of the change in temperature is equal to negative U, 1 over CH, 1 over CC, dA. Now we can take the integral. Yes. Yes, indeed. So that will get us natural log of change in T2 divided by the change in T1 is equivalent to negative U area 1 over CH plus 1 over CC. It's looking nicer. From here, we're going to go back to these little expressions we made, and take the integral of them. And so now we're just going to have heat transfer is equal to negative CH delta T, which is that's equal to negative CH TH2 minus TH1. If we do the same thing for the cold, we get positive CC TC1 minus TC2. Put this on my lap. I'm not cheating. I'm just putting it on my lap. And because I can't wrap up here. Yeah. And we have that now. So I'm going to take this and put it over here. Everything's the same color. Plug her in. So we get the natural log of TH2 minus TC2, right? We're doing the change in temperature 2, and he's taking away from the cold. So then this one is just with regards to the first part. And that's equal to negative universal heat transfer coefficient multiplied by area multiplied by TH2 minus TH1 divided by Q. And this is going to be negative because plus Tc1 minus Tc2 divided by Q. Interesting, very interesting. And then so we then can take out the Q. We can factor out the Q. And we get, delta C2 divided by delta T. I know we're putting it back already. And that's going to be equal to our universal constant, Q, multiplied by change in temperature of 2 minus change in temperature of 1. You can also put that over Q instead of taking it out of the parentheses. Either way. We're looking for our heat exchange rate, which is this Q. So we multiply that over and divide by this. This is the log mean difference. So we divide by that log mean difference to get our final heat exchange rate is equal to negative universal. Let me try to write it really nice. That was awful. Great. D2 minus D1 divided by log, or natural log of T2 divided by change in T1. That's not too bad. You should see my handwriting at work. That's even worse. I literally write it in another notebook because it's so bad I know nobody can read it. So I rewrite all my stuff that I cut it down so I also remember it. Rewrite it in nice handwriting. So also if I ever need to show anybody something or explain something to a new person or whatever, I can just refer back to that notebook and show it to them. And I write it in simple terms. But here we go. This is our heat exchange rate. That's beautiful. I know. It's gorgeous. I know. We did all that work. That's not that much work, honestly. Wait, let's see. This is something unrelated. Let's see how much work we do for other stuff. This is for like fourth. So this rate of evaporation, rate of reaction. I feel like we did more. I go to homework 3. See who has the most work while we're out and about. Just a decent. I don't know. Doesn't nothing of this looks like that much work. After it, maybe I erase it. Oh, that looks like a lot of work. But not really. It's not like a lot of work. It's like a decent amount of work. Maybe that's like, this seems annoying to write out. I don't even know what I was doing there. Oh, this is pretty bad. Maybe I just locked in and got better at. What even is that? Whoa, that's interesting. Look at the first homework. Wow. We were really artsy. Okay, let's go back. This isn't this is section 5, but put it in 4. So after that tangent, there we go. That's what we're looking for. Come back. That's what we're looking for. What are you texting? What is that from? Who are you texting? No one? I don't think that's from something. Oh my gosh. Does anyone know? Oh, it's what are you doing? Texting? I think that's the reference. Let's think back to the co-current and countercurrent heat exchangers. This is, you're like, how does this relate? This is a log mean difference, right? Log mean difference with temperature. So it's an LMTD temperature. We draw a graph for our co-current and our countercurrent. We're gonna find something out very quickly. Right, so we start the hot media, right? The temperature of the hot media starts up here and it slowly decreases in temperature. That's not great, right? Because it transfers over to the cold media, which slowly increases in temperature. And our temperature difference at this point, our change T, almost equals 0, right? There's like very little temperature difference. But for a counter current heat exchanger, everything starts at a different spot, right? So our temperature of our cold media might start here and it goes like this. And our temperature of our hot media might start here and go like this, right? So our change in temperature between, it's not a thick pen, so it's bad writing. My bad. Maybe I just have bad handwriting. No, I don't. Yes, I do. So our change in temperature right here is going to be larger than our change in temperature of the other graph. So our change in temperature in the countercurrent heat exchanger is always going to be larger, or not always, but a lot of the time going to be larger than the co-current heat exchanger. So that log mean difference is going to look a lot different between the co-current and countercurrent heat exchangers, and therefore their heat exchange rate will look a lot different as well. Now let's talk about the effectiveness of heat exchangers. Oh, wait. Also, a countercurrent heat exchanger is going to be more efficient for the heat exchange rate because this numerator, since the change in temperature is larger, right? If the change in temperature is larger, the numerator will be larger, which means that the rate will be larger. So the counter current heat exchanger will be more efficient. Now let's talk about heat exchanger effectiveness. So we have our efficiency is equal to our heat divided by our heat maximum. So we're going to look at this in terms of mass flow rate. Why? Good question. Why don't you try to reason it out? I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay, so now that we're done with that, think about it like this. You have your hot media flowing very quickly and your cold media flowing very slowly. The hot media is going to have a better chance of transferring its heat to the cold stream than the cold stream is to the hot stream because of the difference in that speed, so and that mass flow rate. And vice versa, it's the same thing. So that cold stream, if it's going really fast, it'll be able to transfer its heat to the hot stream more efficiently than the hot stream to the cold stream if the hot stream is going slowly. So we'll have our mass flow rate heat capacity. The hot stream is reference to the temperature of the hot stream going in minus the temperature of the hot stream going out, because that's how that changes. It's the right way it changes. Divided by the mass flow rate of the mass flow rate heat capacity, the minimum. And this is going to be the temperature of the hot stream going in minus the temperature of the cold stream going out. Going in, not going out. I hit that again. This is going to be equivalent to our mass flow rate heat capacity of our cold stream multiplied by the temperature of the cold stream going out minus temperature of the cold stream going in, because that's how that one works. It's the opposite. Divided by the minimum once again. This one's going to be the same. So this is, of course, our max heat transfer. I had a coworker named Max. He was all right. It's good. I left that company. Not there anymore. But he was nice. He's kids. In terms of NTU. NTU, isn't that a college? No, that's NKU. You silly goose. Net transfer units. And everyone always says, and it's exactly what you think it means. But half the time I look at this stuff and I go, I don't have a single thought in my head. I don't know what it means. What do you mean net transfer units? That's just 3 words that don't relate to anything in my head. But net transfer units are basically the units of heat transfer that occurs overall. And that's going to be your universal heat transfer coefficient multiplied by the area you're talking about, divided by that mass flow rate heat capacity variable, the minimum. Okay, so that's going to tell you the overall units of the heat transfer. Just how much is transferring, overall. Net. You know net. You know net. I know you know net. What's fun about the net transfer units is that usually these variables are given by the company that you buy the heat exchanger from. So you know these, right? And your company that you work for will go, hey, you yourself will think if you're higher up there, you will think, hey, I kind of want the net transfer units to be this number for it to be, profitable or more efficient in the plant. So you go, I've got a number for this little guy right here. Let me solve for my mass flow rate heat capacity minimum stream. And then you go, oh, found it. Okay, let me change stuff up for that. You can also use the relationship. This efficiency is related to the net transfer units as well. You can use the mass flow rate of the heat capacity of the minimum stream divided by mass flow rate of capacity of the maximum heat capacity of the maximum stream. Oh my gosh. And you can say that, let me move you over. You can say that net transfer units are equal to the function of efficiency. And I'm not going to say this whole thing again, but that. You want me to say it again? Okay. Mass flow rate, heat capacity of members. I'm not doing it. But yeah, it all relates back, right? So you can plug in your efficiency, you can find your heat transfer, you can find your heat exchange rate, you can find your max heat exchange rate, you can find your max heat transfer, et cetera, right? And you can do that for the hot or the cold stream, right? And remember, everything is dependent on that mass flow rate, or a lot of this is dependent on the mass flow rate, because, if the hot stream is going faster than the cold stream, everything's going to be flipped around, right? Or the cold stream is going faster than the hot stream. So yeah, that's how the efficiency works for a heat exchanger. Overall, we learned about heat exchangers. We learned about co-current and current heat exchangers, how to find the heat exchange rate with the log mean temperature difference, and how the countercurrent is sometimes more efficient for the heat exchange rate than the co-current heat exchangers, and that the efficiency we can learn about the efficiency and discover the net transfer units that we want and find that mass flow rate, heat capacity that we need for the heat exchanger, depending on what process you're looking for. I hope you're having a good day or night, or if you're one of my friends watching this because you think it's funny, I hope you're having a good day. I'm exhausted. It's 9:21. I've got to go to Pennsylvania tomorrow for my cousin's engagement. Ooh, shh, don't tell her. Don't tell her. But that means I probably have to film in the car, which is gonna be fun, I guess. I mean, at least I can edit in the car. And then, yeah, I mean, I have work tomorrow. I'll get up at 4. I wake up at 4:30, go back to sleep, wake up at 4:40. I don't need 30 minutes. I only need 20. Get in the car, drive to the gym, work out, go to work, be exhausted. Learn a little something. I'm learning a lot. I'm learning a lot about sleeve plug valves, lined plug valves. It's better. It's a great work environment. Love the people there. They're so fun. Wish there were more women near me. But I think that's always a complaint I have. And not in like a diversity way, just in like a sometimes men just don't get it. Like I'm sitting there and I'm like, ugh. And they just don't get it. Like they're just like, why are you ugh? And I'm like, don't even ask. It's just a girl would get it. If she was sitting next to me, she'd be like, girl, I know. I know it's ugh. But it is what it is. And yeah. Where are my women in STEM? they're in the building, they're just elsewhere. What is it like to work in a male-dominated field? Normal. I don't know. It's fine. It's Cody. He sits there, I guess. I'm tired. There's my hair clip. I left it in here. I've got to pack tomorrow. I'm packing tomorrow. I'm packing right before I leave. I'm getting home and I'm packing in 20 minutes and I'm going. And I'm going. I'm gonna go to the bathroom, unpack my stuff, and leave. And yeah. And yeah. And yeah. And that's it. Amen. Hallelujah.